Section 3.5 is displacement, velocity, and acceleration. This is just another look at derivatives, but in this case we're going to be talking about derivatives with some unit measures. So let's get started. Displacement is distance with direction. Distance is measured as an absolute value, whereas displacement is measured with a sign. So if our displacement is positive 3 miles, that means we have gone forward or up 3 miles, and if displacement is negative 3 miles, that means I've gone backwards or down, something like that. Velocity is speed with direction. Now velocity is also the instantaneous rate of change of displacement, or in other words, the derivative of displacement. So if we have a place on the graph, and the graph is a displacement graph, feet and seconds, then our derivative at a particular spot is feet per second, or velocity. So if I have a graph again that shows my displacement, how many feet have I traveled in a certain number of seconds, then if I find the derivative of that graph, which is the slope of the tangent line, or the instantaneous rate of change, I found the velocity. In the same manner, if I have a velocity graph where I have feet per second measured versus seconds, and I take a slope of it at a particular point here, the instantaneous rate of change of my velocity, I've got the derivative of velocity. My units are feet per second, which is feet per second squared. That's an acceleration unit. And it's the derivative of velocity graph, or we can say it's the second derivative of my displacement. So you can see we're going to be using derivatives to go from displacement to velocity to acceleration. So let's say this is a graph where y is measured in miles and t is hours. So this tells me how many miles I am going based on the number of hours. If I take the derivative of this graph, or if I look for the velocity, and we're going to call it dy dt, remember I could also call this y prime, I find that dy dt is negative 32t plus 37. I'm using my power rule rather than going through the entire definition, which is the limit as h approaches 0 of f of x plus h minus f of x over h. But again, we can just use the derivative where we drop down the power, multiply. So that's my velocity equation, and this will give me the velocity at any point in the graph. So for example, when t equals 1, my velocity would equal negative 32 times t plus 37, or 5, oops, sorry, let's put the 1 in there, 5 feet per second. Don't forget your units. At t equals 2, we get a velocity of negative 32 times 2 plus 37, and that's negative 27 feet per second. So what's happening here, let's say that this is our typical upside down parabolic curve, and at t equals 1, my velocity is positive, which means that the distance is increasing, and then by the time I get to t equals 2, my velocity is negative, which means that my distance is decreasing. So possibly it's a football that's gone up and then is coming down again. Negative velocity would indicate that instead of rising or my distance increasing, I would be falling and my distance would be decreasing. Okay, so either of these velocities would give us an indication back to our distance. Now if we want to find acceleration, excuse the traffic, the corner's busy this afternoon. If we want to do acceleration, I'm going to take my velocity graph, or my velocity equation, and take the derivative of that. So now I'm going to call this dv dt. That gives me my acceleration, and that is going to simply be negative 32 feet per second squared. Now, negative acceleration means that the velocity is decreasing, not necessarily the speed. So if the velocity is decreasing, that means that the velocity could be getting faster, but in a negative direction. This should be recognizable to you all as the pull of gravity. Okay, let's try another example here. And actually, let's look at page 94 in your textbook. And this shows what happens with whether something is speeding up or slowing down. If velocity and acceleration are both positive, or if velocity and acceleration are both negative, then the object is speeding up. Now, let's think about this for a minute. If the velocity is positive, that means I am going in an upward direction. And if the acceleration is also pushing upward, this object is going upward faster. The same thing can happen in a negative direction. If the velocity is negative, the object is going down, and acceleration is negative, meaning it's pulling down or pushing down on the object is speeding up. Now, if my velocity is positive, meaning I'm going up, but my acceleration is negative, it's pushing the other way, it's slowing the object down. If the velocity is negative, the object is going down, but the acceleration is in a positive direction, it's pushing upward, again, the object is slowing down. So both velocity and acceleration have to be the same sign in order for the object to be speeding up. It can be speeding up in a positive direction or speeding up in a negative direction. I want to look at one other piece of terminology before we move on here. If my object is in terms of y equals, and I'll just use the same example I had a minute ago, 16t squared plus 37t plus 3, then my velocity, we said, was dy dt, and then we said acceleration was taking the velocity and taking the derivative again. We can also say that this is the second derivative of the distance or the displacement. So if I take this dy dt and take the derivative with respect to t of dy dt, I can also call this d squared y dt squared. So in other words, the second derivative of my displacement equation. So I can either take the terminology velocity and say acceleration is the derivative of velocity with respect to time, or I can say that acceleration is the derivative with respect to time of the derivative of distance or displacement with respect to time, in other words, d squared y dt squared, the second derivative. So again, a little bit of terminology. We will keep talking about this as we go along. The next example, let's back up. The next example in your book, example 1, talks about using a parametric graph, and we will do that together in class. So don't worry too much about that until we get together in class, and we will look at that. So let's go on to example 2 in your textbook. An object moves in the x direction with displacement, so we have y equals 3t cubed, this is my displacement equation, minus 30t squared plus 64t plus 57, and they just want us to look at times greater than or equal to 0. So it asks us first of all to find equations for velocity and acceleration. Take a moment by turning off the video to try to find an equation for velocity. Okay, so velocity is going to equal the first derivative. I'm going to say, let's just use v. V equals 9t squared minus 60t plus 64. And acceleration would be then the derivative of that, which would be 18t minus 60. So we now want to find velocity and acceleration at these different times. So again, do part B with the video off. Okay, at t equals 2, velocity equals, let's see, where did I put it? So we've got 9 times 2 squared minus 60 times 2 plus 64. That was negative 20. V of 4 was negative 32, and V of 6 was 28. A of 2 was negative 24, A of 4 was 12, and A of 6 was 48. And I'm sorry, we shouldn't forget the units on here. Since this is miles per hour here, miles per hour, miles per hour, miles per hour, these are all miles per hour squared. So let's talk about whether or not the object is speeding up or slowing down. At t equals 2, velocity is negative and acceleration is negative. This object is speeding up in a negative direction. At t equals 4, velocity is negative, it's going down, but acceleration is pushing positively, therefore it's slowing down. And at t equals 6, both are positive, therefore the object again is speeding up, but this time in the opposite direction from at t equals 2. Okay, so we've talked about speeding up, slowing down. We've done a couple of examples. I do want to look at example 3 in your book. So let's erase this. Example 3 says the acceleration is given as a of t equals 12t minus 5, where a of t is in centimeters per minute. So this is an acceleration equation, and t is in minutes. So it asks us to take a look and say if the velocity at time t equals 1, so at t equals 1, velocity is 8 centimeters per minute. Well, they're asking me to go backwards. They've given me acceleration, they want me to find velocity. So, since a of t is v prime of t, a of t is the derivative, I can find v of t by thinking about what equation could this have come from. Well, it's got to come from a t squared because I dropped the power. What number would have to be in front of this so that when I dropped the 2 down I would get a 12? So it would have been a 6. Minus, this would have had to have come from a t, and since there is no power to bring down there, it would be 5t. The problem with this is that although this is, although this is the antiderivative of my acceleration, remember when we have a constant here at the end, it just disappears? So I don't know whether or not there was a constant or what it might have been. So I know that v of t is going to be something like 6t squared minus 5t plus or minus a value. The question is, what will that value be? Well, they gave me some information. At t equals 1, v of t, or the velocity, was 8. So let's see, we've got 8 equals 6 minus 5 plus c. 8 equals 1 plus c, so c is 7. Therefore, my velocity equation was 6t squared minus 5t plus 7. And that's my final velocity. So we've taken velocity, looked at derivatives to find acceleration, and now we just looked at acceleration and worked it backwards to find velocity. The key is we've got to find this plus c value. Now this is called the indefinite integral. So if g is an antiderivative or indefinite integral of f, then g prime of x equals f of x. And that's what we just did with velocity. Why do we call this indefinite? Well, because with that plus c at the end, unless we're given further information, we can't find the definite integral. And that's what we were doing earlier on in the year. One last thing. This is on page 96 in your book. If x is the displacement of a moving object from a fixed plane, and t is time, then, and this is just kind of a recap, velocity is x prime or dx dt. Acceleration is v prime or dv dt, or x double prime d squared x dt squared. And the other thing that I just want to recap for you is that speed is equal to the absolute value of the velocity. We don't often talk about speed except when we're talking about speeding up or slowing down. Okay, that's it for 3.5. 3.6, let me just do this real quickly for you. 3.6 is just a definition, and it says that the derivative of sine x equals cos x, and the derivative of cos x is negative sine x. We will work on problems on these together in class. You just have to memorize these. Do you hear me? Memorize them. We will do some problems in class together. That's it.